Last time we were talking about uniform quantization, and we had derived that for r bit quantization levels for r.
Sir, are you sharing your screen?
Yes, is it not visible?
Some might be a problem on my end then.
Oh, no, this thing. Okay, I'll unshare it and I'll share it again. Now is it visible?
Yes, sir.
Excellent. Okay. Yeah. So we were talking about uniform quantization. We had seen that for r bit quantization, there are, oh, sorry. There are L equal to 2 to the power r quantization levels. And this introduces a quantization noise such that plus k, where k is a function of the distribution, right? So now, having derived this, let us talk more about SQNR. So if we talk about SQNR, we see that this is the ratio of the signal to noise power or signal to the quantization noise power. But say I have a signal. Suppose I have this signal, fine. And these red lines represent the quantization levels. So what happens now is if I quantize this signal, then this, this, so for low, the quantization noise is, or the quantization noise power is constant right? We had seen this in the last class as well, that the quantization noise power is constant regardless of the signal amplitude. Agreed?
Yes, sir.
So, but if the signal, say I speak at a very mild voice on on this thing. If I speak at a very mild voice, the number of quantization levels that I actually use will be small. I'm I'm intentionally speaking at a low voice right now. So the number of quantization levels that I use will be small. I won't be utilizing all the quantization levels that are available to me. But what that will do is that it will have, even for a small number of quantization levels, it will have the same amount of quantization noise. But since the amplitude range of my voice is low, it won't be actually. Yeah, so not, right now I used a large number of quantization levels. So if I use a large, instead, if I use a larger number of quantization levels, the signal to noise ratio that I will get will be better. So if I speak low, then my average signal to quantization noise, or if I speak at low volumes, my average signal to noise ratio will be worse than someone who speaks at high volumes. Agreed?
Yes, sir.
But it shouldn't be so, ideally. Everyone, regardless their amplitude, should get the equal signal to quantization noise ratio. That's what you would want, or you would want that uh, you get the same quality at lower signal to at lower signal amplitudes as the same quality as you get at the higher signal amplitudes, right? Or you would want that lower signal amplitudes should have more quantization levels than higher fine. Or if I draw it like this, then say in this range, I have more quantization levels, and as the amplitude increases, the number of quantization levels starts becoming smaller. This is what we would want. See, you want, if you have something, as when you are measuring gold, you want it to be more precise because it's in micrograms, or you would want to measure it in micrograms or milligrams or things like that. But when you are buying rice, you can afford the magnitude of error to be within a few grams or even tens of grams. But when you are buying gold, you cannot afford the magnitude of error to be even in a few milligrams or several milligrams, right? So the
Yes, sir.
magnitude of error should depend on the amount of the quantization values, or the amplitudes. So obviously, I'm not telling you to use the same scale for measuring gold and rice. That would break a gold scale and would not register on a rice scale. So anyway, the point is that we want more quantization levels at lower amplitudes and less quantization levels at higher amplitudes, and this process is known as compression, or we want to compress the signal. such that, say that if, or we want to use a uniform quantizer to use uniform quantizer to get this non-uniform approximation. So one option to do this is to use quantize 1 plus k, or rather log of 1 plus kx instead of x. We know that log of 1 plus kx looks like this. So you can actually have a large number of quantization levels. So smaller variations in the amplitude will correspond to larger quantization level, a larger number of quantization levels. And as you increase the amplitude, the number of quantization levels corresponding to that range of amplitudes will reduce. Agreed?
Yes,
Yes,
sir.
sir.
Yeah.
Sir, but
So yeah,
even if my even if the signals at higher amplitudes,
yeah,
since they have lower number of quantization levels, won't
yeah.
it? I mean, how would we differentiate what they actually were?
So the good thing is that they are susceptible to a or higher amplitudes so there's no straight away there's no mathematical modeling for this, but the key idea here is that as you increase the amplitude, the sensitivity to the exact amplitude reduces. Like I
Okay,
said,
sir.
that's why I gave that gold and rice example. You buy 5 kilograms of rice, or you buy 5 kilograms and 10 grams of rice. So those 10 grams of rice are irrelevant at 5
Okay,
kgs.
sir.
But 10, if you are buying gold, 10 grams of gold will set you a lot poorer. So even 1 gram of gold will set you a lot poorer. So the sensitivity to the amplitude in quantization actually reduces as you increase the amplitude. So this process is known as compression. And to reconstruct the signal, we use an expander. Generally, and this whole process of compressing and expanding a signal is known as expanding. Generally, instead of the signal x, we quantize the signal v such that v, absolute value of v, equals fine. The base doesn't matter. And
So this is called as compounding.
companding.
Companding.
Yeah. So this is just something that you should know. And I'm just looking for the, yeah, mu equals for practical telephone companding, or for PCM telephone, this mu takes the value 255. There is also something called the A-law commanding, where this is non-uniform, non-linear, and or and obviously this is for normalized. Both of these are for normalized amplitude. 2, 1. So these are also is close to 100 for practical purposes. So actually, companding is a good idea for your grading as well. What say? I can take the log of something, and then higher grades all get bunched into one, and lower grades get better resolution. So
So
yeah,
you can definitely try that out.
yeah, I'll see. So yeah, this week's quiz I have uploaded the marks, and there was a correction that some people in one set I had not I had not marked one question incorrectly. So I had marked one question incorrectly in one set. So I have corrected that. So is the quiz okay now, or do you have still have some problems with the marking? Okay, I presume that it means that the quiz is okay. So there is this topic on line codes. So 7.9, Simon Haken. I have covered sampling, quantization, and I leave the encoding portion for you to read. There is not much to discuss. And we come to the last topic in the 7th chapter. So the quantization process is slightly complicated because we have the quantizer, and the design of the quantizer is slightly complicated. So we try another way of doing things that is known as delta modulation. We know that band limited signals are highly correlated and therefore change very slowly. The difference in two adjacent samples, if taken close enough, is agreed. Do we agree on this?
Sir, why
Yeah.
are they correlated?
Okay. Yes. So agree. Yes. 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 So this we didn't. Uh, so uh, I would instead of the mathematical details, because we don't have the bandwidth to go into those kind of details now. I would rather say that if you look at a practical signal, such as a picture that you send via your cell phone is a practical signal. We agree on that.
Yes, sir.
So you take that picture, you say, if I look at your profile picture specifically, so it's a pattern, purple, blue, and something like that. So what you would say if I take an arbitrary pixel, so it would be some picture in 1024 cross 1024 pixels, let's assume. Fair assumption?
Yes, sir.
Yeah. So let's assume that it's a 1024 cross 1024 picture. It's a circle though, but I'll assume a square. And if I pick a pixel at random, there's a high probability that the next pixel will have the same value or a value quite close to it,
Well, you close to it.
right?
Hmm. Okay.
Or if
Sir,
you look at my profile picture, for that matter, I don't know which one is visible. The blue one where I'm looking at the wall like an idiot, or the black one. So anyway, if you look at my picture, there's a lot of there's a lot of black and there's a lot of skin color, and so anyway, what you will notice is that if you at any point, if you the points close to it will have quite similar values, the pixels, right?
okay, sir. So this is saying that meaningful pictures uh,
Meaningful
have
pictures have
nearby pixel. Okay, sir.
slowly varying pixel values. That is what I mean to say.
Okay, sir.
So meaningful picture or even meaningful speech, it doesn't vary at 4 kilohertz. The actual rate of variation is quite small. So uh, what is meaningful actually doesn't require. So if you look at speech and sampled at 4 kilohertz, if you sample speech at 4 kilohertz and or even if you sample speech at 10 kilohertz, suppose, you'll see that adjacent samples vary quite slowly. It's only over a large amount of time that the samples show a significant difference. So adjacent samples have only this delta change. So an
Okay.
idea that was introduced was that let us fix delta, and instead of quantizing two samples, or instead of quantizing each sample, let us quantize the difference between between adjacent samples as delta. So let us quantize just the difference between the adjacent samples. So and let us sample at high rates, say 10x the Nyquist rate. So we notice that if we sample at say 10 times the Nyquist rate or 5 times the Nyquist rate, the variation is slow. Say then x NTS, or rather x NTS minus x n minus 1 TS is small. Fine. Let's say this is ENTS. So ENTS is small. Now let me use a 1-bit quantizer for this. This and let's say E hat NTS equals delta if ENTS equals, or if ENTS is greater than 0, minus delta if ENTS is less than 0. Fine.
Yes,
And
sir.
x hat equals x hat n minus 1 TS plus E hat NTS. Fine. So if I start at 0, so say this is the signal. If all the signals say suppose start at 0 and I sample at a rate large enough, then this delta modulation, so say this is delta. Plus delta minus delta plus delta plus delta plus delta plus delta minus. I should be able to follow any signal using this, right? I should be able to follow any signal using this delta modulation, sampled at a large enough rate. Okay.
Yes, sir.
Yes, sir.
And this is simple to analyze. Agreed? This is so not mathematically analyze, but this is simple to construct.
Yes, sir.
So what we are doing here is our trading off the sampling bandwidth, but we will require more bandwidth to transmit this,
Yes, sir.
or we'll require more. We are trading off the sampling bandwidth for simplicity. Again, no free lunches.
Sir, simplicity and one more thing, I think here only we need 1-bit quantizer, right?
Yes, 1-bit quantizer. That is the simplicity.
Okay, 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 sir.
That 1-bit quantizer is the simplicity. So the block diagram of a delta modulator can be given as X NTS this is the comparator plus minus delta. So this gives you this X hat and minus 1 TS because you actually compare it with the past estimate. E hat, yes, this you transmit. And here you have this sorry, this is a delay here. Delay TS. X hat NTS. So you give in X hat T NTS, you get minus 1 TS. Get this plus plus. So this is the accumulator, and this thing, the entire structure is a delta modulator. Fine.
Yes, sir.
And the demodulator is simple. So if you look at or rather, I call it E hat as right.
Sir, the first symbol has to be separately transmitted, right?
The first symbol you assume that you start at 0.
Okay.
If you assume that you start sampling the signal because every signal rises from 0.
Okay, sir.
That is so what you are talking about is DPCM or interlaced video coding. I'll just speak about that. We won't derive the mathematics of that thing because this is an important topic otherwise, but we don't have the bandwidth to discuss that in this course right now. Otherwise, I would have in a full offline class, I would have discussed DPCM as well. So this. So, oh no, this you don't need this. Simply add a delay here. TS. Fine. This is fine. This is the delta demodulator. This is a
What is
demodulator
the
for
what
sorry
is
M. Sorry, this is X. The book uses M, so I got confused. I used X.
sir, is that a delay?
Yeah, this is a delay.
Oh, okay.
I just got lazy. So this is basically the accumulator. So a delta modulator contains the delta demodulator. Fine. And you trade off bandwidth for. So yes, this is okay.
Yes, sir.
Now delta modulator has two inherent disadvantages, or there are two problems. Delta modulator. One is called the slope overload noise. That is, if delta by Ts is greater than Tt, then the delta modulator will not be able to follow the message signal. So you see that this delta modulated signal can only change at a rate delta over Ts. The rate of change in time, since every Ts, it changes by either plus delta or minus delta.
Yes, sir.
So the rate of change of a delta modulated signal is delta over Ts. So if the rate of change of the true signal, that the one that we are trying to follow using the delta modulator, if that is greater than the rate of change of the delta modulated signal, then
Sir,
we actually have.
shouldn't it be opposite? Or
Oh, sorry. Yes,
no?
you're
Oh,
right. Yes, if it is less than. So this was the condition that delta over Ts has to be greater than this. So then the delta modulator will not be able to follow the message signal. So if the rate of change of the delta modulated signal is greater than, is less than the rate of change of the signal that we want to modulate, then we are in trouble. The delta modulator won't be able to follow the signal, and we will get something like this. Fine. So one condition on delta modulator is, that's why Ts. Fine.
yes, sir.
And the other one, if I have this, this, it will never converge to the true value of that signal. It will continue to oscillate around this. So if delta is too small, then you won't be able to track the signal properly. But if delta is too large, then you will just oscillate around the true value of the signal. So this is called, this is slope overload noise. This is called granular noise.
Sir, can you explain granular noise again?
Yeah, so say you have a constant like signal. So this signal goes to some constant value after a point. So at
Yes,
one
sir.
point of time, the approximation is greater than the true signal. At the next point of time, the approximation is less than the true signal. You see
Okay,
that?
sir. Okay, sir.
So At one point of time, it's greater, less, greater, less. It will never reach the true signal. It'll just oscillate around it.
Okay, sir.
That is granular noise. Because so this, you see this as a grain delta. So the larger the grain, the more will be the granular noise.
Okay, sir.
These are the two problems with delta modulation. And there is something called adaptive delta modulation.
Sir, in delta modulation, we compare the incoming, say, X of NTS
Yeah.
with the previous true
Estimate.
X of estimate
No,
or the true
with the
value? Oh,
previous
estimate.
estimate.
Okay, sir.
In actual, the idea is to compare it with the true thing, but you do it with the estimate because the receiver will have the estimate.
Okay, sir.
Okay. Adaptive delta modulation, we vary the step size with. So this is just an idea that I'm throwing because we have like 15 minutes and I want to finish something else as well. So I'll just run through this one last thing. So we, yeah. So we vary the step size with, so if we get repeated plus deltas, so if we get multiple plus deltas one after another, we are sure that the amplitude is too large. So we use a larger delta. And if we get this 0101 kind of a thing, we assume that we are facing granular noise and we decrease the size of the delta. So that is known as adaptive delta modulation. I won't be going into the details of that. Again, you can see that the granular noise in delta modulation is delta square by 3. This you can derive using whatever we did for quantization. Fine.
Can you so adaptive delta modulation, we vary the step size with?
We vary the step size with the input. So I'll just I'll write granular noise up here. Adaptive delta modulation with the input. Input. If we get 1 1 1 1 1 1 1 or 0 0 0 0 0 0 means the slope is either repeatedly increasing or decreasing, and we have a slope overload. Fine. So we increase the step size.
Okay, sir.
If we get 10 10 10 10, which means we are oscillating about the same point, we decrease step size. Fine.
Yes, sir.
Great. So this is delta modulation. So actually we ran through delta modulation, to be honest. So out of the official topics that I discussed or that I wanted to cover, only detecting a binary signal in noise is remaining. That I don't know whether it will take one lecture or 1.5 lecture, but I don't want to risk that. So I'll finish everything else today. So if we are able to finish this detection of binary signal in noise tomorrow, then your vivas can start on Friday. If you guys are ready. Anyway, we'll discuss this after I finish this. So the last topic, DPCM. In delta modulation, we exchanged bandwidth for simplicity. What if we exchange simplicity for the bandwidth? So Bhavnik, now I am answering your question. The correlation is neither an assumption or nor can it be proven mathematically. It is something that is physically observed, like the Newton's laws of motion. You cannot derive the Newton's laws of motion out of anything. They are there. Or I am talking only about non-relativistic frame of reference. So when you talk about non-relativistic frames of reference, you say that Newton's laws of motion are there and everything else is derived out of those. Similarly, the correlation is something that is physically present. You can observe it like gravity. And based on that correlation, our job is to optimize the systems or optimize the energy and bandwidth usage. I hope that answers your question. Just send a thumbs up. Yeah, excellent. So now the question that we are facing is that there is a large amount of correlation in images. So say I've possibly said this earlier as well. Each pixel on an image. So if you go to it in an RGB image, if you take RGB image, say I'll say that 16 megapixel. 16 megapixel RGB image means each pixel is 3 bytes. R is 1 byte, 8 bits, G is 8 bits. So each pixel is 3 bytes. We agree on that? So that way, a 16 megapixel image would be 16 into 3, 48 megabytes. You take pictures out from your phone camera. Most of 16 megapixels cameras are common these days. So is a 16 megapixel image 48 megabytes?
Sir, the raw one is probably.
Yeah, raw one is 48 megabytes, exactly 48 megabytes to be precise. So there's this thing called code. Similarly, music is sampled at 44, because our auditory range is 20 to 20 hertz to 20 kilohertz. So music is sampled at 44.1 kilohertz and quantized at 16 bits. This is what is known as CD quality audio. So 44.1 kilohertz and quantized at 16 bits. So 44.1 into 10 to power 3 into 16 bits means 2 bytes. So per second, you are basically second 88.2 into 10 to power 3 bytes or 90 kilobytes per second, which means a 1 minute audio approximately fine. Is it so? No, it's 1 minute audio or 5 minute audio is generally this size. 5 minute audio is also good. 5 minute good quality audio is also around 2 megabytes practically, right?
Yes, sir.
So what we are using is this correlation. Since adjacent samples are highly correlated, we can get away by transmitting just the difference, or
Okay,
we
sir.
can get away by quantizing just the difference. And if we quantize just the difference is small. So we can use a smaller number of bits to quantize that. So JPEG, MPEG, JPEG is picture experts group, joint photographic expert group, and MPEG is moving pictures expert group. All these standards are developed out of this correlation. That and this correlation allows you to save all that bandwidth and save all that storage space to allow for better, yeah, uh, all that storage space to
Sir,
allow you for, yeah, Deepak.
so every type of compression is this autocorrelation only, or there is different ways of
It
compression
is
also?
based on a correlation.
Okay.
It is the idea comes from correlation.
Okay.
Okay, so obviously this JPEG uses something called discrete wavelet transform that uses properties of correlation and bends them substantially. So is there an elective on multimedia signal processing?
We don't know yet, sir.
Okay. So anyway, that digital communication course, the first topic that we'll discuss there is compression. So I hope so we'll talk about compression in that course. So with that, so actually the mathematical formulation of these things is slightly complicated, and or this correlation based models, the mathematical formulation of those things is slightly complicated, and I would rather leave that to a course on image processing or speech processing or multimedia signal processing. So that take that as a cliffhanger for if you are offered a course on multimedia signal processing, then do that to know how compression works. Digital communication, we'll look at compression from a information theoretic point of view. So this is okay.
Yes, sir.
So one last intuition for this course before we discuss tomorrow's, we discuss detection of binary symbols in noise, which is the closing topic. So all throughout this course, we are talked about transmitting information from the source to the destination. Right. I'll discuss this after we discuss detection of binary signals in noise. I would want to know what is information. Take one day, think about it, and tomorrow we will talk about what is information. Fine. Just only caution is that I shouldn't be given read out answers. I want intuitive answers. Don't Google it. This is not a quiz. There are no marks for this. There are no what do you say? There is no credit for this. I just want your intuition on what is information after you think about it. Fine. So should we let us stop here and we'll take up the last topic tomorrow.
Bye and thank you, sir.
Bye.